Weird team, we are ready, and today we're proud to present you parameter tuning of random forest using design of experiment. And the problem we're investigating is the random forest. Random forest is a powerful classification algorithm that needs fine-tuning. We need to tune all these parameters, and we have 7 parameters in total. And we want to identify, firstly, the most influential parameters, and secondly, an optimal parameter setting, and also a good model, given a hard data set and an algorithm that generates cross-validation scores. And we are going to have a constraint of a budget of 35 runs. And we're going to do this analysis through a design of experiment and data collection and analysis. So for the design of experiment, we want to consider main effects as well as two-factor interactions. And thus we have 2 levels for each parameter as shown in this table. And if we have unlimited runs, we could do a full factorial design with 128 runs. However, since we only have 35 available runs, we can do a fractional factorial design with 32 runs, and we can leave the rest of the runs for confirmation experiments. So here's the factorial design. On the right, you have the design itself, and on the left, you have the correlation plot. The pro is that we don't have any alias among most terms. However, we have some alias two-factor interactions shown in the plot. So we want to estimate all two-factor interactions because they might be significant, and optimal design comes to the rescue. And we're proposing an I-optimal design with 32 runs as opposed to a D-optimal design because it will have better prediction accuracy. So here's the optimal design. And on the right, we have the design itself, and on the left, we have the correlation plot. The con is that we will have partial alias between most terms. However, we can estimate all terms right now because they're only partially aliased, and all VIFs are below 5. And so we are recommending optimal design because our goal is to have inference on all parameters.
To analyze the alternative design, we plot the color map to check the collinearity. The map shows there's minor partial alias among main effect and heavy alias among the interaction terms. However, there's no such problem between main effect and interaction terms. Overall, we still choose I-optimal design because most parameters in this alternative design have 3 levels, but we only have 22 runs, which makes more quadratic terms with less chance to be estimated. Besides, we can have a maximum number of 35 runs to test the experiment. We don't need 13 runs to do a confirmation test, which is very economically inefficient. After confirming to use I-optimal design, we convert the coded level to the actual level. Then we collect the cross-validation data by using cv.rf function with datasets named hearts. The CV data is shown in the table here. In order to find the most important tuning factor that drives the cross-validation accuracy, we first fit the main effect and the interactions between 2 factors into a linear model. The summary of the full model shows only 3 variables are significant under the level of 0.05. Then we create a new model by only fitting those 3 variables. The summary table of this simplified model shows all of them are significant. Therefore, we use this model as our final model.
Check the model assumptions. We plot the normal QQ plot, and a few points depart from the straight line, so the normal assumption is not perfectly fulfilled. However, our sample size is 32 can guarantee the good approximation because it can follow the central limited theorem. Therefore, our model inference is unaffected. Furthermore, the residue and fitted plot does not show any significant pattern, so we can conclude that the variance of the residues is constant with different levels. We do not construct the residues and run order plot because the built-in function of cross-validation can guarantee the randomization and the independence. The adjusted R-square is also a good metric for measuring model accuracy, and our model shows 75%. It explains as much percent of the variance of the data as possible. To this end, further investigation is needed, although it is sufficient yet not optimal. We conduct 3 additional rounds to validate our previous conclusion by randomly choose the factor setting from the rest of not used rounds in the 4-factorial model. The random factor setting are shown in the first table. Then we use our model to predict the cross-validation accuracy and compare our prediction with the actual response. The absolute difference between them are all smaller than 0.5, so we can conclude that the predictions are good. To conclusion, our design worked well, which does not contain any significant correlation, and our model worked well with assumptions have been fulfilled, and it includes most important tuning parameter of the random forest and be able to predict cross-validation values with the desired accuracy. And here's our recommendation to maximum the accuracy of the cross-validation with the 3 significant parameters. For the further experiment design, if the maximum number of the tests could be larger than 35, we can consider to include the quadratic effects to build a better model.